Welcome everybody to the fourth and last series of lectures within the Putinar Online Learning Week. I'm the chair of the session. We hope that you spent a nice summer break or winter break if you are on the southern hemisphere. We hope that you have not been quarantined and that you are healthy. Today, Mihai Putinar gives the first of his 3 lectures on moments. We are very happy that Mihai has accepted to deliver his lectures. He graduated in Bucharest in the 80s. In the 90s, he joined the University of California, and since 1997, his chair is at Santa Barbara. In addition, he held a chair at Nanyang Technological University in Singapore between 2013 and 2015, and since 2014, he is additionally a professor of pure mathematics at Newcastle University in the UK. He received many prizes and grants. I think it's too much to mention it here, except if you want me some prize to mention now. We were very happy when he accepted to give this series of tutorial lectures. It was initially planned as part of a learning week in Constance, and due to the coronavirus outbreak, this became the online learning weeks, and we are still proud in Constance that our servers host this web conference. I would like to remind you that you should please turn off the microphone and camera, except of course Mihai. But you are strongly encouraged to ask questions in the chat. You can open the chat and Mihai will perhaps answer most of the questions at the end, I guess, unless there is something urgent when he might immediately react. So now we can finally do mathematics, and this is Mihai's speciality. So please, it's your turn.
Okay, thank you very much. It's a pleasure to be here. Sorry for the conditions, but we have to adapt. I hope everyone is well. I recognize quite a few people in the audience I know. Hello to everyone, be well. I'll start today. I have to warn you that originally we planned 6 lectures and I trimmed to 3. And what I want to show you are some not so known or not so widely used today parts of the moment problem, some facets which are historical, as important as optimization and real algebra, what you saw in the previous lectures. The basic question is why the moment problem has such a vitality, and it remained on the desk of workers in mathematics, physics, engineering for 200 years. And I have no easy answer to this, except that is a question which was at a crossroads of many currents. And being probability mechanics, algebra analysis, I'll try to touch only a couple of these facets. And of course, I'll be happy to see comments. I'll provide the references in the file which I provided Lynn. You have quite a few of historical articles, and I would tell you what to browse, not to read, and if you have the curiosity, what to experience by yourself with a pencil in hand. So let's try to start my slides. I'll put this in full screen mode. Do you see the slides? Okay.
Yes, we can see them.
Excellent. So today I will speak about continued fractions, which is the royal way, the royal gate to moment problems, and the major contribution of Stieltjes and how it was extended by Hamburger. So it's very classical, very interesting, and as I said, it invites you to put your hands on some simple examples. So first, there were numbers. We start with Euclid division, two positive integers, and we divide them successively. And as you know, we end up with the greatest common divisor. And we can arrange this nice string of divisions into a continued fraction. So the rational number we are looking at can be written as a succession of fractions. And I'll use for today a kind of standard notation. This fat k is the continued fraction, is a simplification just of notation. Now, this was known a long time ago. If the continued fraction finishes, it's of course a rational number. If it doesn't, it's irrational. And apparently the proof of the irrationality of square root of 2, the length of the diagonal of a square of length 1, was proved this way by the Pythagorean school. And here it is, long time ago, the observation. I don't give you the geometric detail. I'll mention reference. Simply the length of the square diagonal divided by the side is this infinite and very nicely periodic, mixed periodic continued fraction. So we have a proof of irrationality of square root of 2. And later on, the algebraists understood this very well, and you can formalize it, for instance, as Bombelli. You take an integer which is not a square and try to compute the square root, as I indicate here. You will see immediately that this gives mixed periodic continuous fraction. So the whole idea is that you have this x, the excess to be an integer, and it satisfies a quadratic equation. You write it as a Möbius transform of fixed point of a Möbius transform, and you repeat. And we'll see soon that this will converge. Now, what is remarkable here, and as you will see or probably know, is that...
Und so entstehen ja noch Geschichten, die sich weit verbreiten im Internet und überhaupt keine, eigentlich gar keine, keine Wahrheit dahinter steckt. Da muss nur eine Zeitung.
I could not hear you very well. Yes? Can you write a message? Sorry. So, as you know, every real number can be expressed as a continued fraction in a unique way. So there is no ambiguity as in the decimal representation. And what is remarkable already here is that the mapping from this sequence of integers to real numbers is not only bijective, but is a homeomorphism from the product topology on the integers to the usual metric topology of the reals. Now, you know the difficulty of defining the reals and filling all the gaps with Cauchy sequences, limits, and so on. And this is remarkable because it gives you continuum in terms of discrete entities, the entries. And this is where we'll return when we'll pass to functions. So already this is quite substantial. What is difficult with continued fractions are the algebraic operations. Addition, multiplication is quite involved. But on the other hand, the topological structure, as you see it from here, is fully contained in the expansion of a real number. Now, there is a simple algebra. We repeat, and I'll put also the division two coefficients here rather than one. There is some ambiguity here when we take continued fractions, and the convergence, as they are called, the partial fractions, Pn over Qn, are defined by cutting this process at level n. And this was very well known to Wallis, Braunkner, and Euler was a big master of this algebra of continued fraction, as we'll see. So there is a simple three-term recurrence relation between this convergence, and strangely enough, the numerators and the denominators satisfy the same finite difference equation, but with quite different initial data. So these are things which, relations which have to be proved by induction, but it is less than 1 page, half a page. Let's suppose we have the convergent Cn, then simple manipulations, I'll not do them here, gives you the full limit in terms of this convergence. So that's pure algebra. And what is remarkable is that if all entries, as in the case of numbers, are positive, then the sign of the difference between two consecutive convergences alternates. Now, if you played in school or if you are teaching limits, you remember that if you define sequences by recurrent relations, most of the time you have this phenomenon that you will have a monotonicity of the even and a monotonicity of the odd, and kind of squeeze couple of sequences, as it is the case here. So already this is interesting, and it gives us an idea of the convergence of this process. Now, as we saw, square root of 2 periodic continued fractions are very special. So if we stop at a certain moment, we get the same result as going to infinity. And obviously, they satisfy a quadratic equation. And this was proved back and forth by the founders of modern algebra, Euler, Lagrange, Galois. I'll not go into these details. I'll give you examples. I want to show you where it leads to functions. And now, Fermat problem, the famous Pell equation, asks to solve in integers this simple Diophantine equation. D is an integer. And simple observation is that if x1, y1 is a solution, then taking n powers of this element in the extension field, we call it now, we obtain another solution. Indeed, one line proof, you see it from there. Well, why I mention this? Because there is a continued fraction behind this simple observation, which gives you the finite term relation from taking the powers, as you saw before. And immediately representation of the inverse of the square root of d in terms of a continued fraction. Well, Lagrange proved that these are all solutions, and it was a very big deal. There are a lot of studies in number theory on the Pell equation, and to provide a complete set of solutions is quite remarkable. And speaking about this, and this is a first message I would like to give to our colleagues who are listening. Why continued fractions? They offer always the best rational approximation of the respective entity. So far they are numbers, but soon they will be functions. So if you are looking for problems where you have to approximate, this is the optimal way to do it. And there is a very simple manipulation of the recurrence relation, which gives you immediately why it is so. That the convergent satisfies what Lagrange noticed is the best gap between a rational number and the given real number, and this characterizes the nth approximant. So that's something which gives not only the best approximant, but looking at the speed of this convergence, transcendence criteria for all kinds of numbers. I have to mention Markov because he did a lot of work on moments. He started his master thesis, as you see, we jump over centuries here, with a very deep analysis of the continued fractions of Lagrange, so-called Bernoulli sequences. And he got a lot of intuition about this approximation from there. And then all probability, Markov processes, and so on were derivations of his understanding of the continuous fraction. So far, we spoke about numbers. Let's move on and see a little functions. Here is a very simple observation of Markov. Let's reverse the roles and start with a quadratic equation. We want to solve it using this mechanism of continued fractions. And immediately we notice that if we do algebra, z is 2 plus 1 over z, we repeat, and we get the solution, 1 plus square root of 2. But wait a minute, this equation has two solutions. What do we do wrong here, and where is the other one? Well, if we try to understand what is going on and put the other solution we know from basic algebra, the approximants of when we cut and we replace with the other solution will not converge. So already we have an interesting phenomenon here that for some values of the parameters, the fraction converges, for some others, does not. And this was understood quite well in the time of Gauss and later Riemann. And here is a divergence test, which I put it as a tutorial at the end of these lectures. And I invite you for the next time, maybe you can try to follow the indications and prove it with your means. So if we take, in short, now we leave the integers, we just work with complex numbers. We take an absolute convergence series, the continued fraction attached to it. You can prove by elementary means that even an odd convergence have limits, but they are different. So very interesting. We have a divergence criterion immediately here, which shows two phenomena, that there is a discrepancy between odd and even, and the recurrence relations will give you immediately the divergence. There is a gap between the two limits. On the other hand, the counter-positive, if you want, of this observation is Seidel. Simple criterion again, if all entries in the continued fraction are positive numbers and the series is divergent, then this will converge. And again, this is a tutorial at the end of these lectures, and I invite you to prove it with pencil in hand. Now, why this is important? Pi, of course, one of the most important numbers. We know infinite product representations, for instance, from the sine functions, already knew to Wallis. And at that time, so this is 1650 something, you get a continued fraction expansion of 4 divided by pi. And the analysis of this was the beginning of moment theory and the jump from numbers to functions as we see. So the main idea, to analyze one more time this simple continued fraction derived from the infinite product, is to introduce a parameter and to regard this as the value of the respective parameter at 1, let's say, and to analyze as a function rather than numbers the convergence of the continued algorithm. Simple manipulations, I put here a few lines just to show you the elementary flavor, gives you an approximation of this b, this function, which starts with 2 over pi, and an asymptotic evaluation, which shows that indeed we have convergence and the rate of convergence is low. Now, why I mentioned that moments were born here, because this function, which was used by Braunkner to compute pi, has a series expansion, Taylor series expansion, Laurent series expansion at infinity. And what he did, in fact, was just to apply Euclid division algorithm, not for numbers, but for series in 1 over s. And the result is extremely simple. You can see B of s is a continuous fraction with a parameter. And the convergence is derived from the inequalities, the elementary facts we infer from this computations. So far, so good. So we have functions, we have series, and what is important here, we have the coefficients of the Taylor expansion at infinity of the series and the coefficients of the continued fraction. In closed form, this function, by the way, was found by Ramanujan much later. He was a big master of continued fractions, and this is just a simple expression of gammas. And now the analogy with numbers. We start with Laurent series with only finitely many negative terms. We define the integral part, the fractional part, exactly as we do with numbers. And we have a non-Archimedean norm here, which is just the exponential of the degree, usual common sense idea. And we start the algorithm. So I start with a series and take the integral part, take the inverse, take the integral part, and so on. We find that this always converges in the sense of the valuation we introduced. And a major theorem, which goes back to Gauss, but was perfectioned by Markov and Chebyshev, gives exactly the order of convergence of these partial fractions. So we repeat what we did with numbers with series, formal series so far. And we have this remarkable result. Later on, at the end of 19th century, this was known as Pell approximation and entered much later into the field of applied mathematics, as you well know. Now, constructive aspects, we have the series. We associate to it some determinants. So a matrix, we call it Hankel today, but was known way before Hankel. And polynomial. And as far as Jacobi, it was known that the approximants of the continued fraction are exactly this determinant, which gives in modern terms the orthogonal polynomial associated to the moment data. The numerator is just the integral part of the series applied to the denominator. That's the Pell algorithm. And F is rational if and only if the determinant of the Hankel matrix is zero. I'm sure you saw this in a different context with modern proofs, but I want to stress that these facts were discovered algebraically very early. And Jacobi has a lot of works. His collected works are about 10 volumes, and you can see a lot of accumulated knowledge based on particular series and computations. Now, just returning to the Pell equation, if we do it for rather polynomials than numbers, we end up with, of course, elliptic curves, hyperelliptic curves, and Abel observed immediately that some specific solutions of this will give what we call today abelian integrals, elliptic integrals, which can be resolved in elementary functions. That's quite remarkable. Again, the Pell equation. And in his computations, there were continued fractions. Now, for this part, we have two outstanding references. Is Perron, who wrote a monograph on continued fractions around the First War. And there are later editions in German, and I highly recommend it. And then there is a very recent book by Sergei Khrushchev, who linked the Euler perspective on continued fraction to modern theory of orthogonal polynomials, asymptotic expansions, and things which you know from modern mathematics. I highly recommend them. So far we had numbers and functions, and here comes Stieltjes. This was the major jump forward, and I would say still it's of interest and highly recommended to everyone to read his memoir. I put it in the folder attached to these lectures. and see his brilliant ideas. So Stieltjes had a lot of interests and accumulated experience with particular continued fractions. They were related to the hypergeometric series, to the gamma function. Of course, in secret or not, he was dreaming of solving the Riemann zeta hypothesis, and with these tools. So he had a big understanding of particular situations. And he distilled from there a general framework, which is in his famous memoir. So he starts with now a functional continuous fraction. We have the parameter S. And he's interested only in coefficients which are non-negative. So you can see that all these A, B, and even the complex ones have a real part greater than 0. This, of course, invites, because the continued fraction is a repetition of Möbius transform, to look at one single step, and we remark immediately that such a map preserves the right half plane. So already we are in function theory, and we have linear fractional transforms of a very simple half plane geometry. And there are convergence criteria. They were discovered, of course, by Stieltjes, and later Markov put them in a correct setting. And the point is that if this particular fraction converges to a finite value on a sequence with an accumulation point, then converges everywhere where it is defined. Well, if you know a little complex analysis, this sounds like Montel theorem or Vitali compactness argument, and is a major discovery because you infer from the pointwise convergence at a very thin subset something on the behavior of the function of S everywhere. In modern terms, there is, of course, a compactness argument hidden here, a normal family, but that was not known at that time. And Stieltjes discovered this in a series of fascinating letters to Hermite, and both of them were very enthusiastic that this is a new phenomenon which deserves a lot of attention. And that was the beginning of the motivation of his memoir. So he starts with such a fraction. All coefficients A are non-negative. You remark that we jump from A1Z to A21, A3Z, so the even and odd are quite of different flavor. This can be rearranged into more symmetric form, but this is how Stieltjes started. And he remarked immediately, as we saw before, that the even and odd convergence have limits everywhere in the complex plane minus a semi-axis. But these limits may not be the same. And moreover, he understood, and later was Poincaré who put this in a proper setting, that this fraction has not a Taylor expansion, but a weak form of a Taylor expansion at infinity, called asymptotic expansion by Poincaré, which means simply that if we truncate it, it will become small after multiplying with the respective inverse of the power. So again, here we don't have convergence of Taylor series, but an asymptotic expansion. And Stieltjes remarked that if the series of these coefficients, which by the way are free, is convergent, then the limits exist, as we saw before in the Koch example. They are different. So what is going on here? He, on the other hand, remarked that if this series is divergent, then the continued fraction converges everywhere to a function, and this function is what we call today a Stieltjes integral Cauchy transform, the simplest form. For this reason, Stieltjes invented the extension of the Riemann integral, and this unifies the observations that partial convergence are always rational of this very specific form. M are positive, and so the little m's here, the poles are negative. And then he started looking at integrals of this form as representing asymptotically the continued fraction. And now the comparison, I bring it back again, and this is the second message of today. Before we had numbers, real numbers, we expressed them as continued fractions in a unique way, and we lost nothing. We have the topology here and the bijective representation. Here we have, let's say, positive measures, point distributions, probability distributions, as you like. And we look at the asymptotic expansion of their Cauchy transform into a continued fraction. What is remarkable here is that parameters on the right-hand side are free, are simply constrained by an inequality. They are non-negative numbers here. They are non-negative real numbers there. While if we take the asymptotic expansion of this integral, the coefficients, as you know very well, are subject to a lot of positivity constraints. All these Hankel determinants have to be positive, they're shifted Hankel determinants, and so on. So somehow this transformation freeze finds the completely independent parametrization of the continuum. And now the continuum is not a number, but a distribution of point masses seen as a measure. Now, modern theory, as probably you know, we have, thanks to Ries and Herglot's representation of all analytic functions which preserve the upper half plane and correspondence to positive measures. Such a measure admits moments of any order if and only if, in the sense of Poincaré, we have the asymptotic expansion along the imaginary axis. And then we go full circle, and we have in the previous representation functions, measures, and the parameters in the continued fraction. The moments are somewhere in between the formal expansion. There is a recovery, as you know. We lose nothing if we pass from measure to functions by Cauchy transforms. It's an inversion formula due to, again, to Stieltjes in his memoir. Perron has a little update, and this was the beginning of spectral analysis, as you know, modern terms. Now, Why Stieltjes was so much interested in this? Because of divergent series. And everyone knew and was puzzled by the following observation. We want to prove Stirling's formula. And probably you saw this, you expand the logarithm of the gamma function in few terms, and the remainder is an integral, which, believe it or not, is a Stieltjes transform after some very simple manipulation, and has a asymptotic expansion. The formal series, if you develop this in a formal series in Z, you can, of course, take the Neumann series and replace, will diverge. And this was the big puzzle. But if we stop it far enough, we'll give a very good approximation of the gamma function, and in particular of the factorial. And this was the origin of Stieltjes' work, namely to renormalize divergent series using continued fractions. And instead of their value, so this is the series, use the limit of the continued fraction. So it's a renormalization of divergent series. The moments are exactly there, and the distribution is phi. And this was very successful and understood by Poincaré, by all others, and was a major breakthrough. It is called, by the way, the Stieltjes renormalization of divergent series. Maybe you know the Abel renormalization, Dirichlet, and there are quite a few others, Cesaro, and so on. Now, I jump 20 years. Big master of continued fraction, Hamburger, understood Stieltjes very well and said, well, let's drop a few of the assumptions in Stieltjes' memoir, and let's see what happens if we just take real A's, that's not a major constraint, and complex B's. He proved convergence with a compactness idea at that time attributed to Grommer, now is called normal family argument. He obtained a parametrization of all solutions. So he solved not only the moment problem, but he obtained all solutions looking at the convergence. And he is the first one who identified a quantity which appeared much earlier in orthogonal polynomials, the role of the Christoffel and Darboux kernel. And I suppose you saw Edward Powell's speaking about the magic of the Christoffel and Darboux reproducing kernel. Well, it was Hamburger who put it in the right place concerning the moment problem. And then immediately after, Nevanlina did thorough investigation of these three major articles of Hamburger, again solving the moment problem and having the interpolation theory, what we call now the tangential interpolation theory of bounded analytic functions in place of the convergence theory of continued fractions. So all this were very well understood, as you see, 100 years ago. We are customers of these great people. And I want just to end this first lecture with an observation about the same time of Poya, about the limit theorems in probability theory. I didn't mention probability yet. One of the major questions raised by Laplace was the central limit theorem, which haunted a lot of mathematicians, in particular Chebyshev and Markov, and was not satisfactorily answered and proved until Lyapunov around 1905, I think, found a solution. Now it's well understood. And what it is all about, I don't go into probability, but essentially the central limit theorem is the following phenomenon. We have a sequence of probability distributions which possess, let's say, all moments. And we know that we have a very weak convergence. Then can we infer from this a much stronger convergence? Originally, F was the Gaussian. Fk were distributions associated to sums of independent random variables, normalized. And if we know only that the moments converge, can we say something about the distributions themselves, or the measures? Well, this is the case. And Poya has a very beautiful article, which I included in the files there, stating exactly that under some assumption, which we will see in the next lecture, that this gives a uniqueness of the measure given the moments. So assuming that this superior limit is finite, so these are the moments, then indeed convergence in moments will give you convergence, what we call now weak star convergence of measures. Again, here in modern terms is a compactness argument, much later discovered by Prokhorov. And you have to know that, so as I said at the beginning, the moment problem appeared in renormalization of divergence series, in number theory, appeared in questions of irrationality, transcendence, and also in probability. So just to finish my first lecture, this is what I said before. Here are the tutorials, and I invite you to put a little your imagination at work and prove both Seidel and Koch tests. This will be good a little to understand what it is at stake. I assure you, very elementary in questions of convergence. So I don't go over this. Please try to follow these lines, and let's discuss next time. I'll stop here.
Okay, many thanks for this nice and comprehensive talk. So I guess you got some questions in the chat. I actually did not follow the chat. Maybe you got them privately, or were no questions?
I have Cordian is requesting to annotate. I approve. Just a second. Hello, Cordian.
I'm sorry. I'm trying to figure out how this works. So I'm sorry. I pressed this by accident.
Well, let's take our time. We depend on these technologies.
So it means okay, so it means there are no questions in the chat, right? So
well, maybe it was too frightening, sorry to say.
We still have some time. I mean, we have 10 minutes. If there are some questions,
I'll be happy to give some time to our colleagues to digest this. And next time I'll continue with not with continued fractions, but with function theory. And I'll reserve some minutes at the beginning to discuss these two convergence criteria.
Okay.
So that would be my plan. And please look at the folder I attach. It contains a lot of historical articles. If you have the curiosity and the inclination, read Stieltjes. It's as fresh as would have written today.